My name is Simon van Dijk. I'm going to speak to you guys about how to diagnose cancer with machine learning. So last year I spoke about ants. This year I'll talk to you guys about brains. So this is me. I work at Platform 45. We do design-driven software for web and mobile, harnessing Ruby. Neural networks, I love machine learning. That's like my passion. And in the purple thing there is a logo for a community meetup. So I love learning from the community, and I love the feeling of teaching others when they sort of get it. So I'm going to start off with a little bit of computer history. So just bear with me for a bit. Even though I'm talking about some technical stuff, there's no code or anything that I'm showing you. Charles Babbage. This dude lived in the 1800s, and he invented that machine in the background. It's called the analytical engine. And it was a mechanical decimal calculator. And from what we know, it's general purpose. It was the first Turing-complete machine that's been designed. Charles Babbage himself didn't actually build this thing. They only just recently built it, and it works. He designed it. So he's a bit of a legend to me. There's another person, Ada Lovelace, and she, I don't know what her relationship with Babbage was, but she invented what's attributed to her as the first algorithm. So it's a series of steps running on a general purpose machine that computes these things called Bernoulli numbers, computes a sequence. But the idea was there that they wanted to take something that they were already doing, do it faster with a machine. Okay. That was general purpose. So she's also a bit of a legend to me. And what I'm going to be talking about is basically how in AI we harness models, or how we model things in AI. We harness that ability to get the attributes of those models that we're modeling. So we model the brain. And these are some models that we encounter. A computer was actually a room full of female workers in a production line, and they would do a little sum and then pass it on to the next person, and effectively at the end of the production line they had computed a sum. So that's where the word computer comes from. Desktop is self-explanatory. The server is like an American waiter or waitress, if I understand correctly. And there's lots of others. So the main model we're going to talk about today is the artificial neural network. So a neural network in itself is what we talk about when we talk about the brain. Artificial neural network is our model of this thing. So I want you to consider the smallest part of the neural network, which is the neuron. And biologically, there's three characteristics that we model. There's the axioms, which are inputs, the nucleus, which we replace with a function, and dendrites, which we replace with outputs. So this has some really unique properties. We have approximately 10 billion of these things in the human brain. They're elastic, so they can thicken and they can thin, sending stronger or weaker impulses. And they exhibit these biological states, either excited or inhibited. So it's like 1 or 0. They have this special property. They approximate the generalization of knowledge and discovery, which just means that they learn. It's just Alan Turing actually said, one of my favorite dudes ever, said, instead of trying to produce a program to simulate the adult mind, why not try produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult mind. So he had the idea of taking something unstructured and giving it, telling it when it's right or wrong. And if you model the brain in the correct way, you could actually teach it to do certain tasks. So the neuron, we model with a thing called the perceptron. Okay. So perceptron, the axioms would be represented with inputs. The elasticity, so the thickness or the thinness of the inputs would be modeled with these weights. So you can see the thicker one is larger. And then we have the output and the nucleus, which is simply a mathematical function. So if you replace these things, this is how we get to an output. We take what's called the sum of products, 0.1 multiplied by 0.9 plus multiplication of the others. That gives you net. Net you feed to a mathematical function, which is the nucleus, and the output of that function is the output of the perceptron. So pretty simple. And this is the general case. So you have inputs, weights, net, and then a function, which is just a math function, right? So what we often use for f is a function called sigmoid. Don't worry too much about this, but that's basically what it looks like. It has the domain, which is the x value, from negative infinity to positive infinity, and the range, its output, is from 0 to 1. And that's what it looks like. If we take the example from the previous slide, 0.85, which is net, and we punch it into this function, sigmoid, we get the output of somewhere in that green bar at the top. And those green bars we can use to take that continuous value and convert it to a discrete value. There's another activation function that we use for more Boolean sort of logic or problem, and that's called the step function. So it's what's called piecewise. It's defined with ifs. The output is 0 if the input net is less than or equal to 0, and it's 1 if it's greater than 0. So it's like super simple. And if you put the output on there, you'll get the output of 1 because it's greater than 0. So I'm going to jump into an example. We're going to teach a perceptron to approximate the function OR. So if you use zeros to represent false and ones to represent true, that table in the bottom left shows all the various states that you can get with two inputs. So let's consider the first example. Input 0 and V1 is 0, V2 is 0. We just set our weights to 0 just initially, and let's see. If you calculate net is 0. If you give 0 to that step function, your output will be 0, and that's the target value. So the first pattern, we're okay. We're good. The next one, we have inputs 0 and 1. So we want the target value to be 1, but we have a problem, because 1 multiplied by 0 is 0, so our net is 0. What we can do there is just change this weight to 1, and our output is now 1. So we're good. The next pattern is also problematic, because they're both going to produce 0. So we can solve this by making the other weight 1. Still satisfies the other patterns, but we have the target value. So for this one, we're also good. The last value we get for free. So if both the inputs are 1, both the weights are 1, the sum of 1 and 1 is the net 2. If you put 2 into the step function, you get 1, which is the target output. So congratulations. We have approximated the OR function with a model of a neuron. So you might ask me, why don't we just use a single neuron? Well, it turns out they're limited. So I'm going to demonstrate this limitation by showing you, oh gosh. So on the left-hand side, you see the OR function, and I've made the false values green and the true values red. And on the right-hand side is the XOR function, which is actually the OR function, because the bottom target value should actually be green. You can see in the graph there's 2 greens and there's 2 reds. But what a perceptron does, it draws a boundary in this graphed space. So with one perceptron, we can approximate the OR function, and we can classify the inputs and map them to the outputs. But with the XOR, you can't do that with one line. You need 2 lines, and a perceptron represents a line when you're visualizing it like this. So that's a limitation, but how do we overcome this? It's actually pretty simple. We just compose them, which is effectively what our brain is doing. So you have the inputs, V1 to Vn. Every input goes to every perceptron. That's the middle layer. You can see there's 2 perceptrons there. The output of those perceptrons go to another perceptron, which we call the output. And the output of that perceptron is the network's output. Pretty simple. So let's get to diagnosing cancer for reals. So in order to do this, we need a data set. So you can see each row represents the readings of a single person, and each column is going to represent attributes of those medical readings, and the last column is the diagnosis or the target value. These attributes are real attributes. They take what's called a fine needle aspirate of the mass, and then they photograph it, and then they make little measurements that the domain experts, the medical experts, know are relevant to the diagnosis. So I'm not going to go into training these things because that's actually an entire other field. It's called optimization. And there's lots of fantastic algorithms out there. I just wanted to explain to you guys the basic model. So what you would do is you divide the data into a training set and a generalization set, and you would subject the neural network to only the training set, and you would tell it when it's right or wrong. So you can see in this example, the output of the neural network is malignant, benign, and the target value is malignant, benign, benign. So it gets 75% accurate here. But the optimization algorithm is effectively responsible for this step. Evaluation of the neural network happens as follows. Once you've trained the neural network, you take a record from the generalization set, remember we divided the data, give it to the neural network, it computes those functions with the inputs, and you get an output which is accurate to the training accuracy. That's not, I'm putting quotations here because that's not exactly true, but I won't get into the different nuances of neural networks right now. So effectively what you're doing when you train a neural network is you need to use a search algorithm or an optimization algorithm, and there's many of these. I'm not even going to talk about these, I'm just putting words up. Neither is this talk actually supposed to be used in production. I wrote this code in Ruby to appeal to Rubyists, but if I had to do something like this, I would probably choose SciPy. Just the sheer number of support you have there is awesome. So I'm going to do a quick demo. I put this little thingy up on Heroku. You guys see that? Cool. So I'm going to tail the logs. And I'm going to hit your train. There's a bit of explanation, basically what I've said here. Train. Let's actually do a fresh train. And if you look at the logs, it's going to start a training simulation. And this is just to demonstrate the training. I've actually saved the weights of a pre-trained neural network to classify the stuff. There's one finished. Prints all the weights. In the UI, it's going to say it's done sometime. Okay. And then the step evaluation. So we expect this data set here, this record, basically, of the generalization set to classify as malignant. So if I say classify, it takes that, loads up a neural network with the pre-trained weights, calculates the output, which is just maths, and then returns it to the UI, which is pretty cool. It's a benign classification. And over here, you can actually, if you go to a medical doctor, I don't know how to get these readings, but you can get these readings of your own mass paste it in here, classify the measurements, and it says benign. So yeah, that's the demo. So the thing is, cancer is this destructive force. It's hurt a lot of people that I care about, and I know it seems like an insurmountable problem, right? I actually get like a bit, when I think about it. But the good news is diagnosis of this thing is solvable. Like these techniques, this thing, the classification problem, is actually an extremely easy thing for an AI to do, for machine learning algorithms to do. And this talk is not about how you can use this in production, how you can, like make money off this thing, but it's just to demonstrate if we can put up a little web service that can diagnose cancers with high accuracy. And this is an easy thing for it to do. You can do it with Bayesian learning, statistical methods alone. But if this is easy for AI to do, like what else can it do if you have the data? So I just want to mention what I call stochastic machines. So if we go back to the beginning, I mentioned Babbage invented a machine to do what he was already doing, but faster. So he built a deterministic fast machine. And that's what computers are. They're deterministic, sometimes, right? What if we thought of machines as different to this? What if we thought of machines as we were more lenient with them? We were like, it's okay, they can be slow, they can be sometimes wrong, but let's task them with something else, like look after my grandmother, or things that we already do, but don't have time to. Not looking after your grandmother is, I'm digging myself into a hole. So I just want to ask the question, what tasks could we give machines if we thought of them differently, if we thought of them a little bit more like us, a little less like robots? And I want to leave you with this quote by Alan Turing. If a machine is expected to be infallible, it cannot also be intelligent. So I don't know what that means, because he also said, if a machine thinks differently, how can we say it's not also intelligent just because we think differently from each other? Cool, thanks guys. I'm Sci-Fi on Twitter. There's a demo, it's a gem that does like all the processing, and there's a web component that exposes it as a web service. And that's my email if you want to contact me. Do you guys have any questions? Yeah. So I asked, what training algorithm did I use to train the neural network? I used the particle swarm optimizer. So it's a model of a swarm of birds, the global optimization technique. Anybody else? Yeah. Oh, that was just to demonstrate. Yeah, depending on the data set that you have, the number of attributes will be the number of inputs in your neural network. Yeah. Yeah, I mean, if we had to take this literally for the Zora example, we would have V1 and V2, and 2 perceptrons to draw those classifications. Anybody else? Yeah. So what's the cost of training the... Sorry? Of processing? It's negligible. Look, a lot of the data the data that we deal with in our day-to-day, the valuable data, is temporal, right? It changes. So a hot topic of research is how do you keep the neural network weights trained or up to date when your data is changing every day? There's many different solutions to it. There's nothing really elegant. But training a network every day on fresh data is negligible. I mean, the train button that's on the website it's just to illustrate the fact that you need to train it before you can evaluate it. You know, I mean, you wouldn't actually expose a button like that. Yeah. Anybody else? Cool. Thanks, guys. Good luck.
No come electro por la vida.